Okay, so I think we can start. So my name is Lucio Marcenaro. I'm from the University of Genova. I'm currently the chair of the Autonomous System Initiative of the IEEE SPS, Signal Processing Society. So it's my pleasure to introduce our speaker today, that is Nir Shlezinger. So this is a webinar in the webinar series of the ASI that is going on since a couple of years. And the good news today, before starting the introduction, is that the ASI, the Autonomous System Initiative, was extended. So will be still alive for 3 more years. So there will be a lot of opportunities to have with us a lot of interesting speakers for a great webinar. So please be sure to be with us also for the next webinar. So let's introduce our speaker today. So today we are doing a hybrid webinar, in the sense that is both online but also in presence here at the University of Genova. So I'm happy to introduce Nir Shlezinger, that is assistant professor at the School of Electrical and Computer Engineering in Ben Gurion University in Israel. Nir was a postdoctoral researcher in Tachyon between 2017 and 2018, and between 2019 and 2020. Was a postdoctoral researcher at Weizmann Institute of Science, working with Professor Yonina Elder. Nir received the PhD in electrical engineering from Ben Gurion University in 2017, under the supervision of Professor Ron Dabora. So his current research interests are model-based deep learning, wireless communication, signal processing for communication, information theory, dual function or other communication system, federated learning, power line communication, and adaptive signal processing. So today's talk will be titled Model-Based Deep Learning in Signal Processing and Communication. So I leave the floor to Nir.
So since it's hybrid, I'm gonna put the laptop's camera so close to me, so that to some extent you can both see me and I can see the people here in the classroom. Guys, thanks for coming. Lucia, thanks for organizing this. Thanks, Raj, for your help with this. So, yes, my name is Nir Shlezinger. My talk is entitled Model-Based Deep Learning in Signal Processing and Communications. And it is essentially about deep learning. And deep learning, as we know, is something that has kind of revolutionized our lives over the last 10 or so years. We like to think that it's something that came out of the blue somewhere around 2012 with the ImageNet competition and AlexNet's ability to really get incredible results there. And since then, it's everywhere. All these scientific sci-fi visions of science fiction visions of AI, they're mostly based in deep learning. But deep learning is actually based on ideas that have been around for quite some time. These are ideas of using machine learning models, namely algorithms that learn their mapping from data, that are based on models that imitate the operation of the human brain. These ideas have been around since the 1940s, since the Pitts-McCulloch and neuron, and have been studied quite extensively over 1950s by Rosenblatt and Woodrow and Hobbs. But I guess the major breakthrough indeed happened somewhere around 2012, when deep neural networks, convolutional neural networks, shown to be extremely capable in computer vision tasks. And since then, many other applications have been revolutionized. And we're really not that far from the day where our coffee machine would beat us in any data science competition. And if our coffee machine has access to ChatGPT, then it already does and beat us in every data science competition. Deep learning, we're used to think of its great success stories in mostly 2 domains that are computer vision and natural language processing. All those wonderful success stories that we're hearing with LLMs are essentially fall under the category of natural language processing. YOLO and those kinds of wonderful computer vision models, they all fall under computer vision. And those disciplines have something that is common to them, These are problems that are very difficult to tackle with anything other than data-based approaches. We don't have very good statistical models for the probability of an image-given cat. But there are problems in which we do have very good statistical models. For instance, in signal processing, applications, in control. These are areas where we have very well-established statistical models, and we're used to designing algorithms based on how we describe the environment mathematically. However, as famous statistician George Box said a couple of years ago, all models are wrong, but some are useful. So those classic algorithms that we like that rely on these statistical models, they tend to be quite inaccurate.
Excuse me, can you hear me?
Yes, I can.
Sorry to interrupt you. We cannot, the slides are not progressing with you, sorry. We can only see the first slide in the presentation.
So it's very good that you've interrupted because we actually checked that beforehand. But let me see if it is, let me try to reshare. Thank you very much for letting me know that.
Of course.
Great. Now we can see.
So you've missed all the funny slides. Oh, that's a shame. What's the best ones? Anyway, now my clicker doesn't work. Okay, I'll just work with my mouse. Okay. So what this talk will be about, it will be about hybrid methods. Methods that rely both on data that has its pros and cons, and methods that rely simultaneously also on knowledge, which we know has its pros and cons. Because in signal processing, in communications, we usually have both. We have both data and we have relatively accurate statistical models. So what this talk will be about is about hybrid techniques that combine preclinical mathematical models with data-driven systems. This is what we call model-based deep learning. Now, let me put this more in the machine learning classical terminology. So in order to formulate this from a machine learning perspective, we need to combine what we mean by model-based, what we mean by data-driven, and then kind of say it in the context of inference tasks, compare them, and then combine them. So if we open the Oxford Dictionary and we look at the definition of inference, it will tell us that the inference refers to the ability to conclude based on evidence and reasoning. That means that we're in the sense of an actual system, not a system that I have to predict, but it's based on a set of observed variables. Now, to make this relatively abstract idea somewhat less abstract, but slightly more mathematical, and I'll go to the standard textbook by machine learning by Shlezinger and Viterbi, and they define inference as a mapping from an input space into a label space. And the input space is what we process. For instance, it can be RGB images for an image classification task. It can be tabular data of house locations, which we need to map into their prices. And the inference mapping is a mapping from this input space into the label space. And the set of possible inference rules is referred to as the inference rule space. Now, while this may appear quite abstract, one has to still determine what makes an inference rule good and in what sense is it good, so that you can prioritize one over the other. Now, the classic approach assumes that there's an underlying distribution. There's a statistical model relating what you observe to what you need to map it in. That's what's called the data generating distribution. And another thing that you need to define is you need to give a cost function, a loss function, some kind of a penalty to an inference rule that is applied to an input compared to its desired output. That allows you to assess the quality of applying an inference rule once. Based on the statistical model and the loss function, one can formulate what's called the risk function, which is just essentially the expected loss over the data generating distribution and what makes an inference rule a good one, if it's good in the sense of the risk. The goal is to design an inference rule which will minimize the risk function. That's essentially the goal in machine learning. However, now the question is, how do you do that? The classic approach, the model-based approach, actually tries to tackle this heads-on because it assumes that you have some kind of a knowledge, a characterization of the data generating distribution. So if you actually have a statistical model, you can formulate the empirical risk, and it essentially boils down to some kind of an optimization problem. Whether you can solve it or not, that depends on how complex it is. If it's relatively simple, let's say it's a linear Gaussian model, like we love so much in signal processing, then it may be something that we can tackle. But it may also be may be solvable in more complicated but deterministic models, like the ones people often employ in compressed sensing, where you have a vector which is high dimensional but is actually k-sparse. These are a lot of examples of model-based formulations of problems. I would say, aside that, data is still being used often in model-based methods. You often use data in order to estimate the data generating distribution. I will talk about it in a few slides. The data-driven approach, the one which machine learning is concerned, is for scenarios where you do not have access to the data generating distribution. Instead of access to the data generating distribution, what you actually have are samples drawn for it. You have a lot of images, and they're labeled whether they're cats and dogs. You have a lot of tabular data of houses and their actual prices. Now, based on this data, you have to somehow approximate the risk. So you approximate it using what's called the empirical risk. Instead of taking the expectation of the loss, you take the empirical average over the data, the loss, and then you want to try to find the inference rule which minimizes it. Unfortunately, as we know, you can always find a meaningless inference rule that minimizes the empirical risk. That's exactly what's called overfitting. So you have to somehow restrict the space of inference rules. You have to decide on some sort of an inductive bias, and then you kind of need to optimize the parameters of the inference rule within its parametric space dictated by the inductive bias. So that's essentially what machine learning is about. And when the inductive bias is that of a neural network, then it's down to deep learning. Now, if we kind of think about it, we can put it in those relatively comparative paradigm where we compare the model-based approach to the data-driven one. In the model-based approach, we have a statistical model. We have the data-generating distribution, and based on the data-generating distribution, we formulate an algorithm which implements our inference rule. In practice, what we usually do is we take data, we use it in order to optimize, to identify the statistical model. Let's say it's a dynamic system. We're using data to identify the state space model, and then we're using this approximated model in order to carry out our task. The data-driven approach takes a completely different attitude, where it takes the data, it uses an abstract rule, not one which is related to a statistical model, one which is relatively abstract, and uses the data to fit it to carry out its task. So this is purely based on the data generating distribution. This one is based on the data, the empirical rules. Now, model-based deep learning is essentially a hybrid approach, which is not model-based and not data-driven, it's algorithm-driven. So what model-based deep learning approach tries to do, it tries to preserve the operation of the model-based algorithms. However, instead of trying to identify the underlying statistical model, it directly optimizes the inference rule. So it's effectively all about taking classical inference rules and converting them into machine learning models. In that way, you can both use partial knowledge of the data generating distribution and data in order to carry out your task in a learned manner. Now, we have if you look at it from a machine learning perspective, the model-based approach can be viewed as sort of a generative learning paradigm because you use your data to learn the underlying model, while this family of approaches we discussed about in the context of deep learning are discriminative ones, where you directly learn your task. So model-based deep learning is a lot about converting classic algorithms into discriminative machine models. Now, I didn't say, I gave a relatively broad formulation. Let's try to be slightly more specific because there's no one rule. Because it's algorithm driven, there are many ways to design machine learning models from classic algorithms. And they actually vary along the spectrum in terms of domain knowledge that is required or utilized and the amount of data and abstractness which is provided. Because if we look at the spectrum, there are actually a set of methodologies that lie in between. Some methodologies, what they actually do is they convert a classic algorithm, they use a classic algorithm in order to design a neural network. Another family of approaches, they actually take a classic algorithm and they try to parameterize it to make it trainable. Now this is again still very much hand waving, don't worry, we'll go into more concrete examples shortly, but we have quite a bit of literature about that if you want to look a bit further into how you can enjoy the best of both the model-based and data-driven worlds. We have two papers about this, one in the Proceedings of the IEEE, one actually Access. We have a recent monograph about that also has a lot of code examples that are publicly available. So everything I'm going to present here in these slides are also publicly available, and you can go and check it out and play with it yourself. Now, let's go more concrete. Let's try to show what and where we can kind of use these methodologies. So the first approach I'm going to talk about is an approach which uses classic algorithms as inductive bias, as a way to design deep neural networks or trainable architecture, sorry. Now, the main rationale is to kind of take the flow diagram, the operation of classic algorithms, and use it in order to design a trainable model. It can be a neural network, but it doesn't have to be. And the resulting architecture, what you obtain is something which is specific. It's not a generic, it's not an RNN or a CNN, it's something which is specific to the task at hand. Let's see how we can do that. Because there are actually several approaches to design these kinds of systems. And I guess the most well-established one is the one that's called deep unfolding. Deep unfolding is a paradigm that is around for almost 14 years now. 14 years, that's before AlexNet. That's pre-deep learning revolution. And the paradigm looks at specifically at algorithms that can be viewed as iterative processing, mostly iterative optimizers and iterative descent methods. And what deep unfolding, if you look into the basic literature, what it's essentially all about, you take an iterative algorithm, you fix the amount of iterations, and then you convert each iteration to be trainable, and you end up having something that looks like the sequential processing of a neural network. It's not an arbitrary neural network. It's one that was designed based on an iterative optimizer, an iterative algorithm. And if you look at the literature, they usually say that the benefits are faster convergence compared to an iterative optimizer, an increased abstractness, and compared to the deep learning model, it's easier to train, it has better inductive bias, and often also better performance and improved interpretability. Again, high level, let's get even more concrete. Because actually this is still roughly generic. In order to understand deep unfolding, we need to understand how iterative optimization works, because it all starts from iterative optimization. So let's consider an iterative optimizer. Okay, so what's an iterative optimizer? It has an objective, right? Let's say, I don't know, the objective we have here, if you guys are familiar with it, that's the Lasso formulation. It's a very established objective in super resolution and compressed sensing. And it usually means that you have a signal, you have observations which are related to it, and you have some prior on that signal that is sparse. Very classical. Now, the objective on its own has parameters. Because if you guys are familiar with how the Lasso formulation is obtained in a let's say, super resolution, that's not necessarily what you want to solve. You actually parameterize the objective, let's say using this regularization coefficient, which should tell you to what degree should your solution be sparse. So the objective on itself has parameters. Now, then once you have an objective, you formulate usually a descent method. A descent method is an iterative optimizer that at each iteration tries to get a better refined estimate of your optimization variable. Let's say in the context of the Lasso problem, a reasonable setting would be this iterative sub-thresholding algorithm known as ISTA, which is just an application of proximal gradient descent to the objective dictated by the Lasso. And this optimization algorithm on its own has hyperparameters. When I'm saying hyperparameters, I mean parameters that are induced by the solver. Let's say a step size. If you apply a proximal gradient descent, you have a step size. If you apply momentum, you have a momentum step size. If you apply a soft threshold, then you also have this kind of a parameter that dictates the soft threshold. So there are parameters that are not parameters of the problem, but are parameters of the solver. Now that we understand what an iterative optimizer looks like and its levels of parameterization, we can think of three ways to convert it into a machine learning method. And the first approach would be to take to fix the number of iterations and then treat the hyperparameters, the parameters of the solver, as trainable parameters, as if they were weights of a neural network. What you get by this, you kind of make your algorithm operate with a fixed number of iterations and try to make to use data to make it operate as accurate as it can within this fixed number of iterations. Now, this is quite confusing because when we look at iterative optimizers, we like to think of convergence. There's no notion of convergence here, right? Fixed number of iterations, there's no asymptotics here. But still, within a fixed number of iterations, you try to find the hyperparameterization, which gets you the best results based on the data that you have. Now, you don't have to, the nice thing about this is that it completely preserves the operation of the algorithm. You didn't change anything. It's exactly the algorithm you started with. But you can also modify the algorithm by using not only the hyperparameters, the weights of a neural network, you can also use the objective parameters. Namely, each iteration would use a different objective. How come? Now you got something which is slightly more abstract. It looks more like a neural network because it's as if each iteration tried to solve a different problem. And you can also just parameterize the whole thing. Just take this iterative optimizer, just divide it into blocks and replace those blocks with neural networks. So these are, I guess, the three levels of unfolding that one can consider. And because iterative optim solvers are everywhere, in every application we have, we like to think of, we like to formulate, once we formulate things mathematically, we use iterative solvers. So because of that, it has a lot of potential in various applications. So I will show some examples from different applications. The first one I'm going to show is from wireless communications. Wireless communications, I will specifically look at what's called the hybrid beamforming problem. Hybrid beamforming looks at a case where you have a transmitter that has a lot of antennas, but it has less RF chains, less IOs from the CPU compared to the amount of antennas it had. So it has some kind of an analog hardware connecting the antennas to the CPU. The optimization problem that has to be solved is how you tune the precoder in the analog domain and the precoder in the digital domain to get the best communication setup, let's say, in the sense of the achievable rate. So we know, if we know the channel, we can compute the achievable rate for each setting of the precoders. So what we have here is an optimization problem. Okay, there's nothing here that we don't know. There's no ground truth here. Okay, there's nothing, no data needed. It's a well-established closed form optimization problem. That doesn't mean that it's easy to solve. But once you formulate an optimization problem, you can find a relatively suitable solver for it. For instance, when we're looking at this problem, while it is not convex, we can tackle it using convex optimization tools. Let's say a gradient descent or a projected gradient descent. So projected gradient descent would essentially take gradient sets with respect to the optimization variables, which are the matrices, the precoding matrices, and would update them after following by some projection with a given set. So that's a standard application of projected gradient descent. Now that can work, but usually it would require a large number of iterations in order to converge. If you want to solve it rapidly, which in wireless communications you usually do because you have to solve this problem perhaps even 1,000 times a second, then you need to run it very fast. Then the question is, can you perhaps use deep unfolding in order to fix these algorithms to work with a small number of iterations? And that's exactly what you do in deep unfolding. You fix the amount of iterations, you treat the hyperparameters as the trainable parameters of a machine learning model, and then by drawing a block diagram of the algorithm, what you obtain is something that looks like a neural network, but there's no nuance here. But it does have trainable parameters, and it is something that you can optimize with deep learning training algorithms based on backpropagation. And now you can formulate the learning algorithm as one which learns the hyperparameters. So we have a learning algorithm which learns the hyperparameters, and once these are learned, we just substitute them into your optimizer. And that preserves the operation of the iterative optimizer in terms of stability, and flexibility, and it allows you to make the algorithm work the best it can within a given predefined limited number of iterations. And that works very well. I mean, it allows you, for instance, as we show here, you can use, 10 iterations and reach performance which equivalent to that which the usual algorithm with a fixed step size will take thousands of iterations to converge to. Now, one would say, okay, but you can also just sit around and play and tweak those step sizes until you get the best performance. Yes, you can. You're just using machine learning algorithms to do it instead of having your students sit and tweak them one by one. So it's a way to automate this procedure to some extent. Now, but I would say that the fact that what you're learning is an iterative optimizer means that it's very easy to extend it to alternative objectives. Let's say, for instance, you go from a hybrid beamforming to a robust hybrid beamforming. So you have a noisy estimate of your input. That's okay. You just change the objective from a maximization to a max-min formulation. And then you can use the corresponding solver, which for a max-min problem, that may be the projected conceptual mirror props algorithm. And then unfold it, and you can get exactly the same approach and even better performance. Now, let's see if we can understand what are the gains of treating iterative optimizers as deep neural networks. So effectively, what we propose to do is learn to optimize. Use data to optimize your optimizers. But there are more gains to it than just having it work faster. Okay? For once, the fact that you reduce the number of iterations in some domains, it actually has a real world value. For instance, if you think about distributed optimization, if you have a distributed optimization setup, you have multiple agents that collaborate in solving a task. Each iteration is message passing, is communications. So if you want in advance to say, okay, I don't want my agents to communicate more than 5 messages each, then you can use deep unfolding for that perspective and make your agents achieve the best performance they can within this number of communication routes. And not only does it extend very well to distributed optimization, it also scales. In what sense does it scale? If you think about this, when you learn hyperparameters of an optimizer, it doesn't really care about the dimension of the problem. So we can have a problem, let's say a multi-agent problem with 5 agents. You can have it with 7 agents. You can have it with 10 agents. You can have it with 20 agents. Okay? But still, what you learn here are the step sizes. So we can apply the step sizes for different scalability. You can train a system for a small. You can train them, and then you can apply it for a very large. It's inherently scalable, which with deep learning, it's relatively difficult to have scalable architecture. They're usually constrained to a given predefined input dimensionality. Another cool thing that you can do is learn approximated computations. What do I mean by approximated computations? Well, we have an iterative optimizer. It does a fixed procedure in each iteration. In some cases, this fixed procedure can be computationally heavy. Let's say involve matrix inversion. That's exactly the case of the hybrid beamforming case I showed you earlier. What I can do, I can allow my algorithm to do approximated computations and leverage data in order to cope with this mismatch. To say, despite the fact that I have mismatched computations, which I intentionally approximated to reduce complexity, I can still obtain relatively similar performance. And this is, for instance, what we showed here in a very recent work of ours, where we reduced the number of products by 98% and managed to obtain even improved performance simply using deep unfolding. We didn't change anything. We actually ruined our algorithm, the optimizer in some sense, to make it less complex. Another thing that you get here, well, are you guys familiar with adversarial attacks? You heard of the concept? Adversarial attacks, people think of it as a ghost that lives in machine learning algorithms, in deep neural networks. You have this phenomenon that you can take a deep learning model, and while the deep learning model can operate reliably on images, so you can add some really very, very small perturbations, something which the human eye cannot distinguish. And for some reason, it can make your machine learning model work horribly. So people have shown that for computer vision tasks. Let's say you take this image of a cat, you add very, very low noise, and we still see it as a cat, but the machine learning model will think it's a dog. And people have also shown it for like critical systems, like if you have vehicular systems that navigate by this visual signs, you can maybe put like a small stamp on a road sign, it will read it completely differently. People used to think that this is something which is inherent to deep learning models, but when you view iterative optimizers as machine learning models, you can actually attack iterative optimizers with the same techniques that you use to attack machine learning models. And what actually happens is that what attacks actually do, adversarial attack, when you attack an iterative optimizers, you kind of tweak the loss surface. So instead of having a loss surface that has a minima here, you make a small tweak to it that moves the minima quite considerably. And then you end up, you can actually attack an algorithm. But not, okay, so I understand that you can attack, but because you can convert it into a machine learning algorithm, you can also defend it. Because there are established ways to train machine learning algorithms to protect themselves from adversarial attacks. We can use the same when we convert iterative optimizers into machine learning models. Here, for example, we show the trajectory over the loss surface of an iterative solver once it's trained in an adversarial manner or once it's trained with a standard manner, and they both relatively quickly converge to the same point. So what I try to show here is that this approach of converting an iterative optimizer to a machine learning model just by changing its hyperparameters has quite a bit of potential. But this is not how deep unfolding started. Deep unfolding actually started with compressed sensing. Compressed sensing, we looked at the problem I showed earlier, that's for problem, or this is the formulation of the problem, which is obtained by L1 relaxation of sparse recovery problem. Then they looked at the iterative sub-thresholding algorithm, which I showed earlier. They fixed the amount of iteration, and what this seminal paper by Viterbi and Kalman presented in ICML in 2010 suggested to do was to define parameterization which are relatively abstract. They didn't just parameterize the hyperparameters of the optimizers, they also parameterize the objective. So now what you end up getting is just a deep neural network. And so one would say, okay, so why would you want to do that? Why would you want to use this trainable machine learning model over a standard multi-layered perceptron? And the answer is that it's easier to train. Why is it easier to train? It's easier to train because there's a very specific initialization, which you know exactly what happens when you set these parameters to. For instance, if I would set the trainable parameters of this machine learning architecture to this value, what the machine learning model would do is exactly few iterations of iterative sub-thresholding. So if you guys know that initializing neural network usually is key to learning something successful. So you already start with something good and your training will only improve it. And now there's additional values to learning the objective, because there are scenarios in which another objective may be easier to solve compared to the one that you're actually solving. Here's one which we looked at 3 years ago. It's a problem, it's a linear problem. Okay, I'm trying to solve this linear task to find the vector S, which most closely matches the vector X after a projection by a matrix H. Okay, so this is a relatively simple one, but let's say that S takes value in a discrete space. Now, if S takes value in a discrete space, I would probably have to search over all possible combinations of S to find the one which suits your best. So if it's high dimensional, I can tackle it with some gradient descent method and then, do projection on a discrete space. If I want to go with that approach, it is often actually much better to learn a surrogate objective, namely to actually learn a different matrix. Why? But if you think about it, let's say that this is the original objective I formulated, okay? And this would be the minimal or maximal value of this one. But once I project it to a discrete space, that would be the one I'm looking for. So what I can find a surrogate, a competitive age. This is another problem. This is a different problem, but its optimum point is the same once projected on the discrete space as the one of the original problem. But here, I do not have to carry out these projections. So I end up being much, much less sensitive to noise and mismatches. So you can think about it, let's say in a wireless communication setup. It's often useful to learn a different channel than the true one because it may make your decoding or detection problem easier. So this is another thing that you can get by jointly learning the hyperparameters alongside with the objective. Now, the third approach that I discussed was just to use the iterative optimizer to design a deep learning, to replace its blocks with neural networks. Let's see an example, and I'll again go to wireless communications. And in this example, let's look at the MIMO detection. Okay, so there's a set of symbols sent by multiple users. Each one takes value into some discrete set, and we have multivariate observations. So if I'm looking to the textbook, what would be the best way to carry out this detection problem? So let's say the best approach, assuming Gaussian noise and all that, would be to find the maximum posteriori probability, which would boil down to the minimum distance. Okay. However, trying to find this would involve exhaustive search. This is very computationally intensive. So what people usually do is, instead of joint decoding, they do separate decoding. They decode each symbol separately while treating the remaining as noise. And in some scenarios, let's say in a massive MIMO, where we have an asymptotically large number of antennas, you can show that the performance here is equivalent. And when you are not in the asymptotic regime, you inevitably lose in performance, but you can kind of preserve the linear complexity of separate detection while approaching the performance of joint detection using approaches based on interference cancellation. And interference cancellation, what they do, they kind of try to decode each symbol separately while using knowledge of the previously decoded symbols, not to treat them as noise, but to kind of subtract their contribution. So what does this look like in the context of the uplink MIMO setup I showed? Among the wide family of interference cancellation methods, a useful one would be the iterative stop interference cancellation method proposed from the group of John CFP almost 25 years ago, which takes this block diagram. On each iteration, each one of those symbols, first you cancel the interference from the remaining symbol, and then you decode the current symbol. And then you do it iteratively, so that on each iteration, you use the soft information of the previously decoded symbols. And that's a very useful algorithm, assuming that you know your channel, assuming that the noise is Gaussian, and assuming that your channel is linear. Because if it's not linear, you cannot cancel interference by subtraction. However, you can still treat it as an inductive bias. Okay, in what sense? I can look at each one of those building blocks and say, these building blocks, what it actually does, it takes estimates of the interference, it takes the channel output, and it maps it into a soft estimate, into a probability mass function. That's essentially a classification task. So I can replace it with a classification neural network here. Very simple one, a multi-layer perceptron. And what I end up getting is a deep neural network. But it's not a standard deep neural network. It's one whose architecture preserves or is inspired by the flow of a classic algorithm. And now, while indeed you can say, okay, that's just a big interconnection of neurons, I would say that there are some concrete gains in this specific interconnection of neurons compared to just, I don't know, use some kind of array. Okay, so in order to see these gains, well, you have to understand that this modular structure makes a lot of aspects much simpler. First, in terms of training, okay, I can actually train each one of those blocks separately because I know exactly what it's tests. Because I know that this block has to produce an estimate of the first symbol. This block has to estimate an estimate of the kth symbol. So if I know the operation of each one, that will make it easier for me to train. I will need less data. But it also has additional aspects. Okay. First, training indeed becomes easier because I know what are the intermediate features. When you look at the deep neural network, you usually judge it only based on its output. You can know what its input, you can know what its output, you have no idea what goes in between. So when you train it, you only look at its input and output. In between, all hell breaks loose. Here you understand what are the intermediate features. It has to be a gradually improved estimate of your optimization variables. And you can account for it in the loss function. And that makes training much more stable and much simpler. Now, another thing that you can exploit this modular architecture for, I've said earlier that you can train each one of them individually. Then let's say, for example, that for some reason, the statistical model changed, but it changed in a way that only affects part of the architecture. Let's say I have a multi-user MIMO setup, and one of the users has moved, but only one has moved. If I can relate my only specific models of the architecture to specific users, then I may not have to retrain the entire architecture. I may have to only retrain specific blocks of it. And that already makes it much easier to adapt. Another thing that makes it easier to adapt is the fact that I can detect these changes even without somebody telling me that only this user has moved. Because machine learning literature provides us with tools to detect when a machine learning model is no longer useful. This family of methods is called concept drift detection methods. What I can do here, I can apply concept drift detection on a modular level so that I can inspect each model and say, okay, the reason that this whole algorithm doesn't work anymore is because of this specific block. So I need to only retrain this specific plot. And we have a very recent paper that exactly looked into these kinds of techniques in order to exploit modular architectures. Another way you can exploit modular architectures is using what's called hypernetworks. Hypernetworks is a technique in deep learning which uses another neural network to produce the weights, uses an external neural network to produce the weights of another neural. Now, what you can have with these approaches, you can have an elastic architecture that in some scenarios has a lot of models, and in other scenarios has a small amount of models. Let's say if it's a multi-user communication setup, when I have a lot of transmitters, I will need a lot of models, so I will have my hypernetwork produce a lot of models. And when I don't have a lot of users, I can work with a very simple compact one and have my hypernetwork produce a much smaller amount of intermediate models. So I hope I managed to convince you guys that there's a lot of added value, even if all you use your iterative optimizer for is a starting point and what you use is a deep neural network. So I showed 3 different approaches that constitute what's called deep unfolding. But deep unfolding was all about presenting an iterative optimization algorithm as a block diagram. So what we ended up doing was looking at an iterative solver, fixing the amount of iterations, and then saying, okay, this is a sequential processing. I think it looks like a neural network, so let's see how I can treat it as a neural network. But this whole underlying rationale has nothing to do with iterative optimizers. It can actually be work with any algorithm that can be viewed as a flow diagram. So it doesn't have to be sequential. It can be parallel. It can be any other form of block diagram. How can I exploit this for algorithms which do not have this iterative operation? Let's see an example. Okay. So while most of my examples so far were on communications, except for the compressed sensing one, let's take one from array signal processing. Array signal processing, I'm going to look at the most basic problem in array signal processing, direction of arrival estimation. Direction of arrival estimation looks at the case where we have an array of sensors, and we use the array of sensors in order to detect the impinging angles of a set of signals impinging the array. So this is a classic problem in radar, it's a classic problem in wireless communications, it's even in seismology. People are widely interested in these kinds of problems. And as you can just think of it as a mapping of a set of multivariate inputs, represent what is measured at the sensors, into an estimate of the impinging angles. Now, the nice thing about this is that we have very good mathematical models for these kinds of problems. We can, if the signal is narrowband, then we can actually model the relationship between what was transmitted and what was received using a matrix called the steering matrix, which essentially depends on the phase value differences between the elements in the array. And what happens is that the dependency on the angles is encapsulated solely in the steering matrix. This is for a narrowband model. If it's wideband signals, then we have a slightly more complicated one because the steering matrix now also depends on the frequency. But these are relatively well-established models. They just come from physics. Okay, there's nothing too creative about them. It's not something that we have to make up. We had to make up. It's purely physics-based models. And well, if those purely physics-based models hold, then we have very good algorithms to do localization, to do direction of arrival estimation. One of them is the music algorithm. One of the most classic algorithms of array signal processing is the classic music. And classic music essentially gives you some what's called super resolution, in the sense that you can identify angles of arrival with a resolution that does not depend on the number of arrays you have. And the number of elements you have in your array. It only depends on the number of samples you have. And it's based on projecting the signal into a noise subspace and then identifying peaks in this noise subspace. It's a basic, it belongs to the family of what's called subspace method. And it has to impose some assumptions. In order for a subspace method to work, we need the signal to have to be coming from a narrowband model with non-coherent sources. Non-coherent means that they're not correlated with one another. The covariance matrix is if the signals is diagonal, and the array is calibrated. We know exactly the phase difference. And when the assumptions do not hold, and music will just not work, and all those subspace methods will. So the question is, can I make this algorithm work even when these assumptions do not hold? And the answer is, well, I can throw it away and replace it with a testnet or something, but I can also use its operation and understand that what I actually want is a way to get a good covariance matrix. Because if I have a covariance matrix, which I can decompose into a signal and noise subspace, I can apply music. So one way to do that would be to parameterize the computation of the empirical covariance and parameterize the computation of peak finding in the music spectrum. Now, this is something you can do. We proposed it a few years ago. We took the music block diagram and we used it to design a neural network. So this is a neural network, okay? It has a neural network model, neural network model, neural network model, but it's really not a standard one, right? You don't see eigenvalue decomposition inside neural networks. You don't see formulation of music spectrum inside neural networks. So this is a very tailored one to the localization problem. And we show that it can localize very accurately with both coherent sources and very close sources that have very good resolution, and it can overcome calibration arrays. So this one was shown to be very useful, at least on scenarios on which it was trained. But it had a major drawback. And the major drawback that it had was the fact that it didn't provide the level of interpretability that we're used to in array signal processing. What do I mean? In array signal processing, when we use subspace methods, we usually like to look at the covariance matrix and be able to say, okay, it has this and this dominant eigenvalues that belong to the signal space, and we have eigenvalues belonging to the noise subspace. And this allows us to understand how many signals and noise, and we have something that we can look at and understand. Okay? So the problem is that once you convert everything to a neural network, you no longer get a spectrum. You get something which, I don't know, something that the neural network can process, but you cannot look at it and say, okay, I understand what's going on. I understand I have a target here. I understand that there's perhaps a cluster over there. I understand how many sources I have. Why did we get this problem? We got this problem because we converted the entire music algorithm to a neural network, but you really don't have to do it. Okay, you can actually take a very different approach. You only need to be able to compute a covariance matrix. And how do you know where a covariance matrix is good? It's good if you can apply a subspace method to it and get a true angle variable. And you specifically need here a method which is differentiable because you need to backpropagate through the whole thing, but it allows you to convert the algorithm into a discriminative model. So we can, for instance, take Wood music. Wood music is a variant of music which is differentiable. And you can use the fact that it's differentiable to backpropagate through it and have your neural network learn to map input features into a covariance, where covariance is good in the sense that you can apply root music to it. And that actually allows you to get like a clean covariance matrix, as if it was obtained from the desired statistical model. And then when you apply music to it, you get very accurate detection. You get a very good spectrum, okay? If you do, that actually tells you, okay, here I can look at it, I know I have 3 sources. I'm looking at this without the augmentation. I may think that I only have 1 source. I actually get a very good visual spectrum that shows me what happened. It threw all those outliers to be something that one would not distinguish as sources. And once I learn the covariance matrix, I can plug it to any algorithm I want. It can be music now, and then I can get the music spectrum. It doesn't really matter what algorithm I substitute into. So the nice thing about this kind of augmentation, which essentially uses a model-based algorithm to train a deep learning-based feature extractor. The nice thing about it is that it fully preserves interpretability. It's all not only does it improve the model-based algorithm, it also preserves the interpretable operation. Now, what we saw in the last example was essentially integrating neural networks into an algorithm. And that means that what we ended up doing was not designing a whole new neural network or designing a machine learning model. We took our algorithm and we just substituted deep learning models into it. Okay. So while we showed it for a variant of music, let's show another example which is very relevant, for instance, to applications in autonomous systems. And I guess everybody's favorite algorithm in statistical signal processing, that will be the Kalman filter. And the Kalman filter, which I guess is the flagship algorithm of signal processing, is an algorithm for tracking in dynamic systems. That means that we have an observation that evolves in time, a latent state that evolves in time, and we need to use our input in order to track the latent state. We usually impose a statistical model, which is what's called the state space model, which just means that our state evolves in a Markovian fashion, namely each state is statistically dependent only on its previous state, given all the paths, and that our observations are statistically dependent only on the current state in that sense. Now, that algorithm obviously is fun. You have it in every possible dynamic system today. Was used a variant of the Kalman filter. The extended Kalman filter became very famous when it was employed in the Apollo program to help get the spacecraft into the correct orbit. The Kalman filter algorithm proposed by Rudolf Kalman actually looks at a very special case of state space model, what's called linear Gaussian ones, in which the state evolution function is linear with Gaussian noise, and the observation function is linear with Gaussian noise. And for this kind of setting, it actually provides the minimum mean squared error tracking algorithm. And it does that with complexity that does not grow in time. Does not grow in time in the sense that you only require your current observation and your previous estimate in order to estimate the current state. And you can draw it as a block diagram. It looks very complicated, but it really is not. There's this what's called the predict step, which takes the previous estimate and maps it into an estimate of the current state and the current observations. And there's the update step, which takes propagates the second order statistical models to get this matrix that's called the Kalman gain, which balances your previous estimate with your current observation. And this is Rudolf Kalman being awarded the Medal of Science from President Obama 15 years ago. Now, while Kalman algorithm and the extended Kalman algorithm are extremely successful, as I said, they rely on the ability to fully characterize the dynamics as a state space model. And what we usually do when we characterize dynamics as state space models, we have some understanding of the physics. The understanding of the physics comes into play in the state evolution function or the observation function. Let's say we're tracking velocity and position. It makes a lot of sense that the next position will be related to the previous position plus the delta t times the noise. Okay, that's a constant velocity, constant acceleration, whatever. So we have a good at physical models, but everything we don't know, we just call it noise and just put it into Gaussian noise and say, treat it as Gaussian noise and see how it works. Now, the part which really depends on the stochasticity and the part which is sensitive to inaccuracies in these models is the computation of the Kalman gain. So if one was only to parameterize the computation of the Kalman gain with a deep learning architecture, what you would end up getting is a Kalman filter which can learn from data to track in partially known dynamics with unknown stochasticity. It doesn't have to be Gaussian. The dynamics can change in time, because this is not a static computation. It's a computation which is based on input features. So the Kalman gain actually changes with time, while with linear Kalman filter, it usually saturates, converges to a fixed value at some point. So you don't have to enforce any model of the noise. You can learn from data to handle mismatches, and you can preserve the operation of the Kalman filter. And the nice thing about it is that, well, if you compare it to a classic Kalman filter, in scenarios where the classic Kalman filter is optimal, it achieves similar performance because it actually learns to do Kalman. In scenarios where a Kalman filter is suboptimal, let's say nonlinear dynamics, you use the extended Kalman filter, you can actually get improved results. Not only that, it generalizes. You can train on short trajectories and apply on long trajectories. Very hard to do with deep learning models, let's say like a recurrent neural network that we show here. Another gain that you get that you can measure is latency. Now you can say, but Kalman filter is so simple. That's a linear operation. You'd be completely right. But if you think of an extended Kalman filter on each operation has to do local linearization and matrix inversion. And these are often quite computationally lengthy. So what we saw is that often in practice, you can, by replacing the computation of the Kalman gain with a neural network, not only do you get improved performance over a model-based algorithm, you may also sometimes get improved runtime, improved inference speed, as we see here at 5 seconds compared to 9.9 seconds, and much faster than black box model, deep learning architectures. Now, I showed you only gains in terms of performance that you obtain by converting the Kalman filter into dynamic neural networks, but you also have additional gains that are harder to quantify but are more on a conceptual level. One of them, well, first, you can use a very simple neural network. And if you use a simple neural network, you can implement it on simple hardware. What we saw a few years back, we managed to implement KalmanNet on a vehicle control unit of an autonomous racing car. This is something that we did in collaboration with the AMZ team from Chile, and they had a relatively limited autonomy vehicle control unit that they wanted to track the velocity based on sensory data. And they managed to train a recurrent neural network to do that, but it was too complex to implement on the vehicle control unit. They used a mixed Kalman filter, but that was insufficiently accurate to do approximation. And we managed to implement KalmanNet on this algorithm, which was quite successful. Now, not only do you get improved limited hardware, but you also get uncertainty. What do I mean by uncertainty? Kalman filter, the one thing we like about it, one of the things we like about it, one of many, is the fact that it not only tracks your state, it also provides you an estimate. It also tracks the second order statistical moment, the error covariance. So you don't only get, let's say you have a navigation application, you don't only get the position, you also get the uncertainty. Like it's accurate to plus minus 5 meters or whatever. Okay, deep neural networks are very bad in doing that. They don't provide uncertainty because they only learn to map input into a label. And people use Bayesian deep learning and stuff like that in order to get uncertainty. Here, because you preserve the operation of the Kalman filter, you can actually get uncertainty for free because you can convert the Kalman gain into features that are correlated with the error covariance. Another thing you can get is unsupervised learning because you can relate internal features of the Kalman filter into the prediction of the next observation. So you can train it solely with observations. You don't find ground truth. So the best thing to do is supervise, but you can first train supervised and maybe continue in unsupervised manner. And it naturally extends to other types of Kalman algorithms like smoothing and stuff like that. Another family of gains that you get from converting Kalman into a deep neural network is that Kalman is rarely being applied on its own. It's usually being applied part of a system. Let's say you have some visual measurements, and then you apply some computer vision model, you map them into a state, an estimate of the state, and then you apply Kalman filter on top. But if your Kalman filter is trainable, and your feature structure is trainable, you can train them together. Now you can extract features that are best in the sense of your downstream Kalman task. But the Kalman filter on its own may not necessarily be the downstream task. Okay, it may be correlated to some kind of, it may be able to exploit some kind of structures in the data. So we implemented it for graph signals, where you can actually implement a learned Kalman filter in the graph frequency domain. And it's very useful when you have tasks after the Kalman filter, because often you apply Kalman filter, let's say in a control system, you first estimate the state in stochastic control, and then you use the estimated state in order to regulate the system. So you can now penalize your learning task based on how well the control system operates, or we applied it for financial tracking, where there's no really ground truth state, but you can measure how much money you ended up profiting, and it ended up working very well. Not that we implemented it, we didn't get very rich, but we published a paper on it. You can also use it for brain-machine interface, another application which we showed, where you don't really have some kind of ground truth data, but you do understand what the Kalman feature is used for, and you can judge it accordingly. I think I'm going to have to wrap up soon, so maybe I'll skip the last ones, right? I'll just maybe just present these 3 slides, and then I'll go to the final part. So the one last example I'm going to show is very much related to Kalman. It's also a dynamic system, but one should have a discrete state. But if you have a discrete state, then tracking actually boils down to kind of tracking in hidden Markov models. And what would be a useful algorithm for reading Markov models? That would probably be the Viterbi algorithm. Viterbi algorithm, we like to think of it in the context of wireless communications. It's the algorithm proposed by Andrew Viterbi back in the 70s for decoding convolution codes, but it ended up just being an application of a dynamic programming on hidden Markov models, which you can also view it as a factor graph algorithm. But in the end of the day, what does it look like? It converts the operation of it converts the state evolution that we had in the Kalman filter into a Markov model, like a state machine. And then based on that, it does some kind of linear programming. And for Andrew Viterbi, it worked relatively well. It ended up co-founding Qualcomm. If we saw Rudolf Kalman with Barack Obama, here we see Viterbi with George W. Bush. And it operates in the following manner. Okay, let's say for a communication channel, you have you map your observations into states. So you map your input, what it is that you're trying to estimate into a set of discrete states. Let's say 0, 0, 0, 1, 1, 0, 1, 1. And then for each observation you have, you compute the log likelihood, and then you assign a log likelihood value to each possible state. And then you maintain some kind of dynamic programming along this diagram. This is what's called the trellis diagram. So for each observation, I give a log likelihood score, and then I maintain a path which also accounts for the probability of transiting from one state to the other. And at some point, I'm going to have a colliding paths, and when paths collide, I only keep the strongest one. So this is just dynamic programming. And the nice thing about it is that complexity does not only grows linearly with the number of observations. It doesn't go quadratically with the number of exponentially with the number of observations. So this is a very useful algorithm for tracking of a discrete valued state, discrete valued states. And now, in order to understand which part of it is the, I guess, the more challenging part, I would claim that the challenging part is the fact that you need to compute the likelihood. If somebody told you how to compute the likelihood function, then you can just use it for Viterbi. So one of the first works we had in this area was proposing to augment the likelihood computation of the Viterbi algorithm with a trainable neural network, such that the trainable neural network has to learn to compute the likelihoods. And once you compute the likelihoods, you integrate it into Viterbi, downstream Viterbi processing, which is all just linear algebra from something. Now, at this point, I did have few more examples, but I'm going to skip them due to time limitations. But I will reach this summarized slide, which I think would pass the main point of my talk, which is that deep learning is a very useful tool. It's extremely useful for us in signal processing, for us in communications. We like to think of it as magic, but it's not. In the end of the day, it's highly parameterized models trained by massive data sets, usually in a black box fashion. However, if we bring our own knowledge in signal processing and communication of how those problems should have been tackled, our knowledge on statistical models, we can combine the emerging ability to exploit data with our existing ability to exploit statistical models into a hybrid systematic framework, which I presented several methodologies to carry out. And I do think that signal processing communications are fundamentally different from conventional deep learning domains. And I would claim that just taking things that are designed for language or for vision, trying to apply them in signal processing, they may work, but they have certain drawbacks that we may not be able to tolerate in terms of complexity, in terms of adaptivity, and in terms of interpretability. This is why I believe that potential here of model-based deep learning is just, the tip of the iceberg. And at this point, I'd be really happy to take any questions you have. And as I said earlier, the details here I gave were really on a nutshell. All the details are available in our tutorial papers and in our monograph. And at this point, I will thank you guys and be happy to take any questions you may have. Thank you. I thought I'd start, but I mean, all those questions I see online were about the availability of the slides, the recording. So yeah, it is recorded, and Raj can provide all the answers. He knows this not later. Yeah, please.
If we have data, for example, we don't know how that data comes, and if we apply, let's say, Kalman filter, we call it data driven or we call it model driven?
Well, that depends. Depends on what it is that you try to do. Well, I would say
it's a kind of trajectory or a kind of signal.
That depends on what you're trying to recover. I guess the most classic approach, let me go to the specific slide about that. That may take a while. Yeah. Okay. The conventional approach would be, you have a lot of data, what you usually do is system identification, right? System identification means that you impose some model on your state space. You'd say, I have a linear Gaussian state space model. Now let's find a linear Gaussian state space model which is best described by the data I have. Okay, this would be I guess, the more conventional approach to do that. Okay, the approach that I'm advocating here would say, okay, use whatever knowledge that you have on the state space model. Okay, use it, but don't try to estimate it or fill it up. Use your data to directly optimize your filter and not in order to estimate your model. In the machine learning literature, this is the distinction between generative learning. Generative learning means that you take your data in order to estimate your statistical model, and then you use your statistical model for inference. What I'm talking about, the approaches I presented here are mostly geared towards discriminative learning. Namely, you use your data to directly learn your task. You usually get better performance with discriminative learning, but generative learning has a lot of gains on its own. Because sometimes you need your statistical models for more than one task. So we can learn the statistical model, then use it for tracking, imputation, I don't know, smoothing, or whatever task it is that you can. Okay. Yeah.
Thank you for the wonderful presentation. I have maybe two questions. The first question is, can we say that the model-based deep learning is fully explainable with reference to the classical deep neural networks? And the second question is in terms of complexity and adaptability. Complexity in the sense that we're leveraging classical iterative optimizers with data-driven approach to optimize our filter. So, how is observation generated? Do we have sensors that are embedded with numerical optimizers in the process of collecting data? Or how do we leverage it in terms of multimodal, cross-modal signal processing?
Okay, so there are three questions actually. Let me try to see if I can summarize them correctly. The first one would be about explainability. Yeah. To what degree can we say that it's explainable? Fully explainable. The second question is about complexity. And the third question was about multimodality, or how you can harness, I guess, some of the other wonderful features of deep learning in its ability to do sensor fusion so wonderfully, how you can combine them here. So let me start with explainability. There's no one answer here, because as I showed, what we call model-based deep learning is not one technique. It's actually a family of techniques. Okay, there's this spectrum slide that I showed here. So the level of explainability depends on your methodology. Even only for deep unfolding, I showed 3 different ways to deep unfolding. One which is fully interpretable. You actually understand each feature that goes through the system. So that's the level of explainability. If you look at the machine learning literature, people will usually use explainability in order to look at a machine learning model. A machine learning model would be said to be explainable if you can understand how do the input features affect the output. That's what people usually call explainability. But we like, much more advanced levels of explainability in signal processing, because we need to understand exactly what goes on under the hood. And in this form of deep unfolding, you actually understand what goes on under the hood. But once you start substituting deep neural networks inside it, then whatever goes on inside the deep neural network is still not explainable. So for instance, in KalmanNet, you understand all the features, but exactly how the Kalman game itself is computed, still a black box. Okay. In terms of complexity, that's actually quite difficult to quantify. Why am I saying that? Well, usually we like to quantify complexity in terms of number of complex products, right? This is like our favorite metric for complexity. But in neural networks, complexity is dictated by the number of weights. Actually, the complexity of applying a neural network with d weights is the floating point of multiplications. Because usually the activation function for nonlinearities are usually very simple, or what cost your function is the weights. Okay? So one would say that the more weights you have, the more computationally complex your algorithm. So the more highly parameterized it is, the more complex. So in that sense, everything I showed here is notably less complex compared to off-the-shelf deep learning architectures, because it uses much less weights. But then again, usually you have more complex products here than classic algorithms. You usually have more. However, having said that, that doesn't mean that it is slower than classic algorithms. Take, for instance, the example of the Kalman filter I discussed earlier. A Kalman filter, an extended Kalman filter, presumably is very simple. Okay, so let's say in each iteration, the most dominant computation is the inversion of the matrix, right? The predicted observation covariance. You invert it, and then you do the local linearization. Complexity is usually not such a big deal, but these operations are relatively slow, and they're sequential. They have to be done one by one. Neural networks are very easy to parallelize. And you have wonderful software tools and hardware accelerators, which make you apply neural networks extremely fast. And if you try to write the code in Python, you take the same system, you use Kalman filter, and you use RNN, I bet you the RNN will be 100 times faster. Simply because PyTorch is so good at making RNNs operate fast. I'm not saying that what would happen when you implement it in a system on chip, but so we may be able to, make it even faster, or the trade-off would be different. But I would say that particularly when you run these simulations, often deep neural networks are even faster, despite their increased complexity. So I think I had addressed complexity. The second question and interpretability. The last one was about multimodality and about sensor fusion. Yeah. And I would say that these techniques allow you to some extent to exploit this, but not by, none of what I presented here is plug and play. Nothing here is off the shelf. You can just take it and apply it. I would say that every scenario where you can leverage abilities of deep learning, they do that. For instance, if you have multiple sensors, you can use these, and you want to track them with a Kalman filter, then you can use KalmanNet on top of that and have what's some kind of a soft sensor fusion, where you extract features from each, you learn based on those features, and you tune your Kalman filter to be best based on those learned features. So this is something that you can do. And we have done these kinds of things before with visual data and synthetic data, and mostly these are most of the data that we have been working on. And so in that sense, I would say that I believe that it can be useful, but I haven't tried it myself for multimodality.
Thank you very much.
Okay, guys, then in this case, I will thank you once again, and I will thank Lucian, and I will thank Raj for organizing this, and I will thank the guys at home that attended this webinar. Thank you guys that came here all the way to Genova. Thank you so much, and bye-bye.